Hi, I am Junwei Jing, a PhD student from Karlsruhe Institute of Technology, Germany. I am presenting SPR, Scene-agnostic pose regression for visual localization. First of all, I would like to introduce the definition of the camera pose regression task. Given an image of a scene, our goal is to estimate the 6D camera pose of the image. The input of the task should be an RGB image, and the output should be the 6D camera pose, X, Y, Z, alpha, beta, gamma. There are three commonly used paradigms for this task. The first one is absolute pose regression, APR for short. In this paradigm, we need to collect a lot of training images and train a specific model for this specific scene. Since the model only learns the scene-specific features, it cannot be used in other unknown environments. Therefore, APR requires training one model for one scene with bad generalization. Relative pose regression, RPR for short, uses an image pair as input instead of only one single image. The model in this paradigm learns the relative visual features that can be generalized to unseen environments. Although RPR can be applied in unknown scenes, it requires a large database for retrieving a reference image, resulting in an image pair with the query image during inference. Visual odometry, VO for short, also leverages an image pair as input. It predicts relative poses between adjacent frames, for example, frame 1 and frame 2. When predicting the pose of frame 3, VO takes frame 2 and frame 3 as input and outputs the relative pose between frame 2 and frame 3. By adding the previously predicted pose of frame 2 relative to frame 1, we can finally get the pose of frame 3 relative to frame 1. Since VO also takes the previously predicted pose into account, the accumulated drift is unavoidable in open trajectories. Is there a paradigm to estimate camera poses without the disadvantages of APR, RPR, and VO? The answer is yes, and that's exactly the motivation of our proposed SPR, Scene-agnostic pose regression. Given a sequence of images, the goal of SPR is to estimate the pose between the query image and the origin image using the whole sequence. We randomly take one image of the unknown scene as the origin image. When predicting the pose of frame 2, we feed the origin frame and frame 2 together into the model, resulting in the relative translation and rotation. When predicting the pose of frame 3, we feed the origin frame 2 and frame 3 together into the model so that the model can estimate the pose of frame 3 relative to the origin frame. SPR can work in an unknown scene since it learns the relative features instead of the scene-specific features. It doesn't require a large database because it takes the image of the unknown environment as the origin image. Compared with VO, SPR doesn't have accumulated drift since it doesn't use the intermediate predicted results to calculate the desired pose. Besides the novel paradigm, we also create a large-scale panoramic visual localization dataset termed 360 SPR for the SPR task. 360 SPR encompasses 200K panoramas with ground truth poses among 270 scenes. Why is it necessary to use panoramas for visual localization? The reason is twofold. Panoramas enable overlap between adjacent frames, which is critical for RPR, VO, and SPR. Moreover, panoramic images provide more visual information with a 360-degree field of view compared with pinhole images. In this figure, it can be observed that the translation and rotation error decrease when the image field of view increases among APR, RPR, and SPR, proving the necessity of using panoramas for visual localization. This table showcases the comparison of different visual localization datasets. Our 360 SPR contains more panoramas, more scenes, and more trajectories. Apart from the 360 SPR dataset, our third contribution is the SPR Mamba model for the SPR task. SPR Mamba consists of a frozen dino, a local branch for predicting relative poses between adjacent frames, and a global branch for predicting the relative pose between the desired frame and the origin frame. We take 4 images here for demonstration purposes, while the model can handle an arbitrary sequence length. The 4 panoramas are fed into the frozen dino, resulting in 4 features. Except for the first feature, every feature should subtract the previous feature in the local branch, resulting in 3 features afterwards. The three features are fed into several linear layers, followed by the auxiliary translation and rotation head, producing the predicted relative poses between adjacent frames. Regarding the global branch, all features go through several Mamba layers and then only the last feature is selected to be outputted, since the last feature contains information of all previous frames. The outputted feature is fused with the outcomes of the local branch and then fed into the translation and rotation head for estimating the relative pose between the desired frame and the origin frame. SPR Mamba is designed for predicting poses in unseen environments. Surprisingly, in seen environments, gray columns in the table, SPR Mamba also outperforms RPR and VO-based methods and only slightly underperforms APR-based methods. As for the results of unseen environments, green columns in the table, SPR Mamba outperforms all other methods. For more experimental results, please refer to our SPR paper. There are also some limitations of the SPR Mamba model and the SPR paradigm. SPR Mamba lacks of deformable design when using panoramas as inputs. The error increases when the image sequence length is very long. Similar to VO, SPR can only predict relative poses. We are planning to address these limitations in our future work. Thank you for listening.